Welcome back to another explainer. I gotta tell you, I am absolutely thrilled about this one today. We are looking at a literal astronomical detective story, and it's one that was sparked by some really mind-bending recent discoveries from the James Webb Space Telescope. For decades, we thought we had a pretty solid grip on how galaxies and their central black holes grew up together, like it was a settled science. But the JWST has peered deeper into the cosmic dawn than we ever have before, and honestly, what it found has left astrophysicists completely stunned. We're talking about massive structures that, according to our standard models, well, they simply shouldn't exist yet. So let's just dive right into this cosmic mystery and look at the clues, the suspects, and the brilliant theories trying to crack the case.
10 to 30%, right? Just let that statistic sink in for a second, because this is the jarring number that kicked off the entire investigation. When the JWST looked way back at galaxies forming in the universe's first 1 or 2 billion years, it found that the supermassive black holes at their centers made up a massive 10 to 30% of their host galaxy's total stellar mass. And in some really extreme cases, these are objects affectionately called little red dots by astronomers, the black hole actually outweighed the entire stellar mass of the galaxy itself.
Okay, so why is that percentage such a mind-boggling problem? To put it into perspective, let's look at our local modern universe. Around here, a supermassive black hole is typically a tiny fraction of its galaxy's mass. We're talking just 0.1 to 0.5%. Think of a normal galaxy like a huge, sprawling house, right? And the supermassive black hole is just the fireplace right in the center. It makes total sense. But in the extreme conditions of the early universe, we are seeing mass ratios of up to 100% or more. To use our analogy, it's basically like finding a 2,000 square foot house where the fireplace is 1,500 square feet. There is no way that should work. It spectacularly breaks the known rules of cosmic architecture.
So naturally, scientists had to coin a brand new term for the scene of our mystery, the overmassive black hole galaxy, or OBG. And finding these OBGs means our previous models, which pretty much assumed that a black hole and its host galaxy evolved and grew together at a synchronized, steady pace, those models have been completely cast aside. The timeline is just broken. These black holes somehow got incredibly huge, incredibly fast, all while their host galaxies lagged behind. To solve this, the scientific community has put forward two very different suspects.
All right, let's look at part 1, direct collapse black holes.
So our first suspect doesn't actually throw out our standard cosmological model. It just refines it. It tries to explain the anomaly through a highly specific set of unique birth conditions that could really only happen in the extreme environment of the very early universe. Here's how it builds. Now, the standard way a black hole forms is from a dying star collapsing in on itself. But these direct collapse black holes, or DCBHs, they bypass the whole star phase entirely. In the primordial dark matter halos of the early universe, massive clouds of gas collapse directly into these heavy black hole seeds. What's truly fascinating here is SEP 3. Simulations show they don't even need to feed at mathematically impossible speeds to get that big. They actually grow at moderate sub-Eddington accretion rates. The real secret to their massive dominance? That lies in step 4.
Okay, so how exactly do we end up with that wildly lopsided ratio we talked about earlier? It is basically a tale of cosmic starvation. As the black hole grows, it emits this immense energy. We call it black hole feedback, which heats up the surrounding gas. Meanwhile, the very first generation of stars ever, known as population 3 stars, start to emerge. Now, these stars are massive, they live very short lives, and they die in incredibly violent supernovae. Together, the intense heat from the black hole and the exploding stars violently blow the cool gas right out of the galaxy. And because cool gas is the literal fuel for making new stars, the host galaxy's star formation is heavily inhibited. The black hole gets to just keep growing, but the galaxy itself gets totally stunted.
And hey, this isn't just some wild guesswork. Researchers actually ran this direct collapse scenario through advanced cosmological simulations. As this quote from Latif and colleagues highlights, when they simulated these precise conditions, the results were an excellent match to the actual data the JWST collected from specific, extreme early galaxies named UHC1 and GHC9. So this refinement to our standard model successfully explains how these specific suspects got so big, so fast.
Moving on to part 2, a universal mass ratio.
Now you might be wondering, what actually happens to these rogue, overmassive black holes as billions of years pass? Do they just stay completely lopsided forever? The crucial point here is a concept called a cosmic attractor. Recent studies of galaxy evolution show that regardless of how extreme a black hole's birth was, the mass ratio eventually converges to a universal, stable value. It's like a cosmic balancing act. A balance naturally forms over time between the rate at which gas feeds the central black hole and the efficiency of star formation in the surrounding galaxy. Over cosmic time, this attractor mechanism essentially erases the wild birth conditions of these early rogue black holes, neatly bringing them in the line with the tidy galaxies we see in our local universe today.
But what if the standard model is completely flawed? Let's get into part 3, the topological unfolding theory.
Okay, so what if everything we just talked about is looking at the problem the wrong way? The topological unfolding cosmology, or TUC framework, asks us to literally stop picturing the universe as a collection of tiny particle billiard balls bumping into each other. Instead, picture a macroscopic geometric fluid, a kind of vacuum driven by abstract mathematical entities called Fibonacci anyons, rather than standard subatomic particles. It's a completely different, highly mathematical way to visualize the foundation of reality itself.
And here is where this theory tackles our JWST mystery head-on. The TUC model suggests the universe underwent a deterministic mathematical jump, a massive phase transition from a state of k equals 2 to k equals 3. Notice that really sharp vertical leap on the chart? This represents a sudden thermodynamic unfolding that released latent heat and massively accelerated early matter density fluctuations. Under this specific theory, those impossible, overmassive JWST galaxies, they aren't anomalies at all. They are the exact predictable result of this rapid, geometric unfolding of the universe.
Oh, and the TUC model claims to solve a few other massive headaches along the way, too. Have you heard of the Hubble tension? It's that frustrating fact that our measurements of the universe's expansion rate differ depending on whether we look at the early universe or the local universe. Well, TUC proposes that during that k equals 2 phase transition, the physical sound horizon of the universe actually contracted. When you run the math with this dynamic contraction, the conflicting measurements naturally align, giving us a Hubble constant of about 73.1. It resolves the tension without any tricky secondary fine-tuning. It just kind of works out.
Which brings us to part 4, replacing the dark sector.
Okay, buckle up, because TUC makes a really provocative, sweeping claim here: the complete overriding of the dark sector. While our standard model heavily relies on a static cosmological constant to explain dark energy and invisible particulate dark matter to explain extra gravity, TUC completely replaces both of them. It swaps dark energy with topological latent heat. That's the ongoing energy released from that phase transition we just looked at. And it replaces dark matter with macroscopic topological tension. It basically argues that the extra gravity holding galaxies together is an illusion, created by the geometric tension of space-time itself.
So how exactly does this tension play out in reality? TUC proposes that galaxies are essentially literal defects in the universe's fabric, radiating outward from central black holes. Think of a simple spiral galaxy as having a basic geometric twist, or a winding number of 1. An elliptical galaxy? That's a more complex twist of 2 or more. Theorists argue that these geometric twists perfectly map onto the gravity we actually observe. It provides the necessary centripetal force to hold everything together without needing a single particle of invisible dark matter. Wild, right?
So how do we crown a winner? Let's look at part 5, testing the 2 models.
All right, so we've got 2 incredibly compelling, yet vastly different suspects to explain our universe. How will the astrophysics community actually solve this? The answer lies in highly specific, falsifiable predictions that future telescopes and detectors are going to test. For instance, if standard dark matter models are correct, we should eventually detect dark matter annihilation signals, like WIMPs. But TUC predicts we will find absolutely nothing there. Conversely, TUC predicts a very specific background hum of ultra-high-frequency gravitational waves from its phase transition, as well as distinct spatial correlations in the cosmic microwave background. It also predicts that as JWST looks further back, we are going to keep finding fully mature spiral galaxies at extreme redshifts, completely defying the standard bottom-up formation timelines. The race to verify these exact data points is absolutely on.
Which leaves us with one seriously monumental question to ponder. As the James Webb Space Telescope continues to pull back the curtain on the cosmic dawn, what's going to happen? Will its future observations validate our refined standard models of direct black hole collapse? Or will the new data force a total ground-up rewrite of the history, the geometry, and the thermodynamic reality of our entire universe? The stakes of this mystery literally couldn't be higher, and honestly, the sheer scale of what we are about to learn is absolutely thrilling. Thanks for learning with me today on this explainer, and keep your eyes on the stars.